Hey there, math fans. Quick video on surface of motion. Somebody's asking about this on my discussion board as we get ready for an exam. It's one of these questions of you're given the following curve, and you can actually see it below just because I'm into making these visuals. But you're given the curve where the x-coordinate is always t cubed, the y-coordinate is always 3t squared, and the z-coordinate is 6t. I'm trying to put it off the screen. So when you are given that, a natural question is there anything we can do besides calculus? Calculus is really good for analyzing it. Is there anything we do besides calculus to try to visualize it? Well, one way to try to visualize it is to find what I would call a surface of motion. And that's my own kind of term for it, but a surface on which the motion is occurring, just to help us visualize. There are many ways to do that. So the typical way we do that is we do what we call eliminating the parameter. Now in this case, you can actually see, let's play the game a little bit. T is equal to z over 6, and you can substitute. So that's one way to eliminate the parameter. It actually gives a couple things. So you could say x is z over 6 to the third. So it's like a cubic. You could say y is 3 times z over 6 squared. A cubic, this would be a cylinder, meaning it's just extended in the y direction. This is also a parabolic cylinder. Graphing each of those would confine you. They say the points have to be on there. You can even get something more exotic. You could solve for t, and you could say for in terms of x, and so you could say this is x to the 1/3, and then plug that in here or here. So you could say, I guess we already did it with z, but you could say y is equal to 3x to the 2/3. Sometimes there's other surfaces on which it occurs. You can ignore this other question. That's not what I'm talking about. So anyways, the problem here says, assume someone's already done this for you. They found a bunch of surfaces of motion, and they want you to see which ones actually work. That's easier. It's easier because you can just plug in and see. Meaning, if you put t cubed, 3t squared here, and 6t, do you always get 1? And it's easy to quickly say no. So you're trying to say, does everything cancel and you get 1? No. What about this one? If I put a 3t squared here, and then I put a 6t in there, are those the same? Well, this will be 36t squared, and this will be 36t squared. They are indeed the same. In fact, that's equivalent to what I wrote over here. If you take the y and subtract the z, do you always get 0? No. They don't cancel. The last one that's kind of surprising and harder to see is that you can actually combine a few of them. But again, you weren't having to come up with this. You were given the equation. So you say t cubed equals, is it the product of the other two? Absolutely. 18t cubed. The reason I have the visual here is I wanted to show you these. So if we wanted to visualize this, and I tried to make it so you actually see my equations here. Let me just adjust a little bit. It's actually useful, especially with a 3D grapher, to graph these. So let's graph that one. That's that surface, which is pretty cool. This twisted little thing. How about, let's get rid of that. How about this one? It's on there. So each of these gives you a little more information. In fact, it's on the intersection of those two things. Cool. Let's keep going. How about that cube? It's on that cube. See, each of these gives you a little more information. So one way is it's the intersection of a bunch of stuff. That's kind of fun. And all we had to do is check, whoa. It's the intersection of, though, it's on that thing. So anyways, those are the only ones I graphed. Boom, boom. I just thought it was fun. It's on all of those. All right. Thanks for listening.